Okay, so for the quiz, some are I've been check and scoring some students. Let me use the wait. So wait a moment. Okay. So first is about your quiz. Okay, so your quiz two. Uh, I've checked several students, maybe around 30 to, yeah, around 30, no, maybe 20 to 30%. So I haven't checked the other one. Okay. So I think you can wait until maybe tomorrow. Okay. So hopefully tomorrow I will have the results. And you can check through Google Classroom. Okay, check through Google Classroom. Check through Google Classroom, and then um, if you have any questions, okay, regarding your quiz, you want to know more about details about your answer, we can have we can arrange a schedule. Arrange schedule. We can arrange schedule, but I think if you want to have an offline meeting, I will be available on Monday afternoon. If you want, okay, this is just an option for you. Or you can also, if you don't want to meet online, then we can meet just online at the same day on Monday. But let me know if you have questions or you want to know more about your score. Okay. So for offline meeting, I hope you can maximum at a time is 3 students. Okay. So for example, maybe you want to meet at 1:20, and then you bring your friend and 3%. Okay. Maybe a 10 minute until 1:30, and then 1:30 another 3%. Okay. And if you want, but this is optional. Okay. I'm sorry if you hear that sound. I'm not sure how to isolate the sound. It's from my outside of my place. Okay. And if you want to do online meeting, we can do it. Uh, 2 or 3 students at a time. Okay. But of course, this will be, I will share screen all your answer, and if you want to know. Okay. That is about the quiz. And I think lastly, okay, uh, the whole thing about these lectures, okay, the online lectures. I need to find a better way to evaluate. So evaluate. So suppose we have quiz 1, right? Quiz 2, quiz 3, and then we have midterm. We already done quiz 1, quiz 2, midterm, right? And final. Now for quiz 3, what I want to do is basically, well, it can be quiz 3 and maybe quiz 4 here, because we are now in chapter 14 and we still have chapter 15, right? So maybe quiz 3 will be 14, quiz 4 will be 15, but by default, okay, this is still optional, but I will have the quiz 3. But how we are going to do the quiz 3, um, starting next week. So next week we will have a small pop quiz. So it will be every week. So every week, at least one, we will have a small quiz, just 3 questions to 4 questions, maximum 4. This will be small subject, not heavy subject. It will be taken around, maybe around just 10 to maybe 15 minutes. Maybe maximum is 20. And most of the time, I will set the quiz to be, you can open your book or notes if you want. And you just need to fill in the Google form. No need to submit any paper, but I need to see your video, okay? Your webcam. So, and if you want to come, maybe it's okay if you want to come on last 20 minutes at class for quiz. That's fine. So you missed the lecture and you came at the last 20 minutes for the quiz. That's fine. Just come. And we will use this link always for this course. Okay. Okay, this. And then when will be the quiz? This will be random. Okay, this will be random. It can be Tuesday, it can be Thursday, it can be Tuesday or Thursday. I just want to try and evaluate whether this method can help you to prepare and focus. Because I think you need to have a more trigger to have exercise. Okay, I believe exercise from your TA is not really sufficient, so I need to add more. Okay, so probably every week we will have a small quizzes. So we already at chapter 14. So next week, be prepared. It can be Tuesday, it can be Thursday. We will have a small quiz around 10 to 15 minutes. What you need to do is just be prepared at the last 10 or 15 minutes of the lecture. And you just need to fill in the form, the Google form that I will prepare later. Okay. So that's the announcement that I need to talk with you. And yeah, I think that's the first announcement for before we start the lectures. Okay. So if you have any questions, you can ask, or you can you can chat in the chat box. You can type in your question if you want. I will rewrite all the things in the Google Classroom, so you will notice the message on Google Classroom. Okay. So because we are now using more on Google Classroom, I hope you are seeing the Google Classroom. My suggestion is use the app of the classroom. I think uh, that's better. So you will notice directly of the any information, because I think Moodle is not really that flexible, and the structure itself, it's too um, I'm not really that comfortable for Moodle. It's too rigid. I think because Google, they already have their own Google Meet classroom, right? And then it can store in their cloud, and it's already really good. So I think better we are just using Google. So for Moodle, this is just a general announcement, a reminder. Most of the time, the the important announcement will be on the Google Classroom. Okay. Any questions? You can write in your chat box if you want to ask. Okay. You okay? Any questions? No. Okay. If no, then let me stop this and let me show you this. I hope you can see the the tabs, the Chrome tabs. Um, this is a surface, right? You can see that if you are looking from here, this is a parabola, and it's an ellipse. So it's an elliptic paraboloid, right? And if you look at this side, it has a plane, right? It has a plane. And if we are changing our coordinates A and B, we can change it. This is, I believe this is the x-axis, and this will be the y-axis, this one. Yeah, this is the y-axis. So you can change, and when we are changing this coordinate, we can see how the plane will behave, how they will move, right? How the plane will moving. So this is what we are going to learn, how to create the equations of this plane. Okay. Okay, this is called the tangent plane. So in calculus 1, we established the tangent line, and now we will learn more about the tangent plane. Okay, let's go back to the lecture slide. Okay. Okay. Now let me write here. It's chapter 14. Um, let me check the. Yeah, I think we can start here, the tangent plane, or let me check. Yeah, we already have here. Okay, let me just write the conclusions of the tangent plane. Okay, we are continuing the tangent plane. Uh, the equations that we are getting is these equations. So the idea is to find this partial x and find this partial y. And imagine this partial x and partial y is the component that make up the tangent plane. So if we are creating the plane, probably like this, the plane is um, like, for example, if we are looking at this observation here, then this will be our tangent line, and this is the second tangent line, and it will make up a tangent plane, and uh, we can define this plane in equations. Okay, in equations. Okay, if you are having a direct questions to find the tangent plane, for example, find a tangent plane to z equal to x squared plus y squared at 1, 1, 3. Okay. So we can just directly write that our functions is this, and we can just write the partial x first, right? And this will be just 4x, the other is constant, and partial y will be just 2y, right? And then plug in at x equal 1 and plug in at y equal 1. And we get the partial x is 4, partial y is 2. Okay. And we can just write into our plane equations. And you can get the plane equation from here, right? And if you look at this graph here, this will be resulting the elliptic paraboloid, right? How we can get this paraboloid? If you remember the quiz, we have z equal x squared or z equal y squared when y is 0 and x is 0, right? And both are parabola, right? So parabola on each axis, right? So, and if z is a constant, then we will have this will resulting in the ellipse, right? So means we have something parabola. So if you want to remember you have this oid in the last words, it means that it is representing a parabola. It's representing parabola in 3 dimensions. So it has on this side and maybe on this side. And then this part will be the last ellipse. So it will be like that. Okay. Okay. Let me move to the next page, and I will illustrate the same graph. Okay, because we write the because I think it's easy to draw the paraboloid. Okay. So let me write here, and let me make this into that. Okay. Okay. So if I'm zoom in this part, okay, let's say zoom in this part. Probably we are having so it's like a paper, right? Like a paper, and it's cut here, cutting here. So it's like a paper. And imagine the point that we are going to observe, maybe around here. This is just a random, but imagine this is 1, 1, 3, like the questions that I mentioned before. Okay, imagine that being observed, and then at those points, what is the tangent plane looks like? Probably we can draw something like maybe like something like that. So like another straight paper on the tip of the surface, right? Okay. Now this is why I need to draw all of this, because I need to imagine if you're going to take another zoom, okay, another zoom in. So let's say in this part of area nearby this point, let's take another zoom in. Okay. When we look at maybe like that. Maybe it's getting so if you look at, if you can imagine, like maybe you have a paper and you put another paper on top, and when you look at some part of area nearby the tips of the paper that is touching the another paper, if you zoom in, you will see that this is the surface, right? This is the surface. This is the tangent plane. The gap is getting closer, right? The gap is getting closer. Okay. And if you want to zoom in more and more and more, like maybe this part here, if this is the point, we will notice that the gap is probably, if we look at limit, it will approaching 0 at the distance, right? Okay. So if you zoom in, the the surface z is appears coincide with tangent plane. Okay. Now, what we are going to do with this all visualizations, okay? What we are going to do is we can create a method, okay, to approximate, similar like your calculus one, but now we are using a plane. We can create linear approximations. If I'm writing the equation plane from the uh, previously from the previous questions, I can write this. And let's solve this. Okay. Now, this is the plane here, right? And what we have concluded from the phenomenon here is this is a good approximation of the function when the coordinate is near 1, 1. Okay. Like what we did here, the more closer the area is, we will look at that, oh, it's getting closer and closer to distance, these gaps, right? So that is the point. Okay, so you need to have a nearby positions. And then because of this, we can also write the equations as L is the same equation of plane, but we can write it as terms of linearizations of a function at 1, 1. So L is tangent plane, approximation of f at some point. Okay. Okay. This is the concept. Okay. Now I will write some words, some official definitions from the textbook. Okay. But I hope you can understand what does it mean. Okay. Now let me write recall the equations. Let me just write all the equations for the equation plane. Where the zero is the functions of xy. Okay? So we call linearization of f at some point a and b. Okay, that's right. So basically, this is just the same equations with the plane, but we are just changing the terms. Okay. Okay. So it's basically the same equation from here. Okay. This is the z. This is the z0. Okay. And then these equations or it's only work if the function differentiable at that point at AB. Okay. So by definition, if we have z, okay, then f is differentiable at AB. And if we can express the delta of z we can express this delta as so we are changing all the terms of uh, z and x and y become the delta. And actually we will have the epsilon what does it mean, this part, the epsilon and the delta? So if we look at here, recall what we are drawing here. Suppose we have the distance here, right? The distance here is actually what we are going to look at this epsilon. Okay. So when the epsilon, so where the epsilon 1 and epsilon 2 are approaching 0, so this will be approaching 0 as the delta x and also delta y, the coordinate, the change in coordinate is also getting 0. So meaning, this means in terms of the picture before, meaning this is really small, should be really small. Yes, this. So the limit should be going to be 0. Okay, I hope you get the idea from that point of view. So in theorem, so if partial x and partial y, this is exists near the point, let's say point AB, and also continues at this point, then the functions is differentiable at AB. I think all the definitions are similar with calculus 1. The difference is we need to make it into partial forms instead of dy over dx or the tangent dy dx, right? So we need to mention there is partial x, there is also partial y, and if you want to make both exist near the point, and if they are continuous, and it's enough to prove that the function is differentiable. Okay, let's try to look at this all these things into a practical approach, how we can approximate some functions at some point. Okay, let's see here to show that. So first, show that this function is differentiable at its coordinate, and then we need to find its linearization. Then use it to approximate 1.1 and negative 0.1. Okay, this is the functions. This is the point that we need to show that it's differentiable. So let's start to work on the partial. So this is the function. Find partial x. I hope you get familiar to work on the partials. Okay, if you're still having a difficulty on differentiating in terms of partials, you need to take a lot of practice. After this lecture, I will upload the chapter 14 exercise, so you can look some problems there. So basically, partial x, what we are going to do, we are differentiating x. This is x, this is x. We have two components at least, so we are going to do a product rule. So first, differentiating x is 1, and then the other part is just this. And then plus, this e will be e with power of xy, and xy, we differentiate, it's become y. So we have xy, e xy. Okay. And if we want to check the point, we can look up. So we change, this is 1 0 1 0, 1, 0. So this will be 0, this will be 1. So it will be 1. Okay? And then partial y, we only have y component on the right side. So we just differentiate e, and it will be just e, and then it will be multiplied with x, right? So it will be x squared e x y. And again, we can check the coordinate. So it's also 1. And because it's defined as a number, we can conclude that both fx, fy exist and continue at this point. But this is a simple question to make you see the core concept of the partials and then the linearization and how we are using the linears to approximate. Okay, now the linearizations we can write. Basically, the linearizations at this point, it's the same thing as the equation of the plane. Okay, so we can write this. Okay, we just plug in the coordinate 1 and 0. So linearizations, we plug in 1 and 0 to the equations. Let's plug in here. It will be 1, right? So it will be 1. And then plus 1, x minus 1, plus this is 1 and on the y. So we compute this, we are only having x plus y. This is linearizations. Our linearizations. Okay. Now what we are going to do, we can use these linearizations to check the point nearby 1, 0, which is the point 1.1 and the point negative 0.1. We plug in this to x plus 1. So this is just 1.1 minus 0.1. It's very easy number that I prepared, and it will be 1. Remember that when you are doing all linearizations, this is approximate. Okay, it's not the exact solutions, but it's approximate solutions. Okay, if you want to look at what is the true value, we can check. You can check if you have calculator. So true value, we can just plug in directly this coordinate into our equation. So 1, 1 e, and then 1, 1, and then negative 0.1. And if you check, this will resulting 0.9854 something. And of course, this is approaching 1. If you look at some certain angle, it will be approaching 1. Okay. So there will be some error, right? There will be there will be a percentage of error, right? And this is also something that you need to consider. If the questions is asking to make it into precisely, they need to have like 0.01% error. So we can make it, or we can find in which coordinate that is going to happen, right? So I hope you can imagine that. So that's linearization. So from linearization, we will move to differential. Okay, any question from here? I hope you get the point. Okay. Okay, I hope you understand the concept. It's similar with linearization in calculus 1. The difference is we are using equation of plane instead of the linear equations itself. Okay. Okay. Let's let me check here. Okay, next part is the differential. So let me draw the y-axis like in terms of calculus 1. Okay, if there's a curve, okay, any random c like that, and you have any point, let's say a, and then you have you have a delta x, and you have um, the secant line, right? Let me draw the secant line. The secant line like that, and we can have the delta x and the delta y like that. Right? But when we are looking at the point in which we are getting approached by either if we are have p, q, either p or q that getting closer, we can have our definitions of the tangent, right? So for example, if I'm having this is a tangent, if there's a tangent, um, sorry, and then this is precisely become dy. So you need to make sure that now the delta and d it becomes really different. Okay, we can say that the delta is actually the actual change, right? The actual change of y, right? From a from x equal a to x equal a plus delta x, right? It means this y here and become this y plus delta y, right? So the y will be having a plus delta, right? But dy, this is change, the same change, rate, like a rate of change. You can say dy is the rate of change also. This is change in y when you are using the tangent, right? Okay. Okay. So when is delta x, if delta x is small enough, okay, then dy can be used to approximate delta y. Okay, I hope you can imagine that. Like here, what I want to make sure here is when this delta getting smaller, which means this is the line, right? The delta. When this is getting smaller, maybe here, you will see that the delta and dy will be getting closer, the value of dy and delta, right? So we can also look at the delta and d. It can be it's similar to what we have done before, like a linearization. So it will have some approximations. Okay. Now, if you are talking about all with this d here, so everything with dy, dx, this is we call differential. I think I mentioned this differential in in calculus 1. Whenever you have equations, and inside those equations you have some terms b in terms of rate of change of something, we can say that this is the differential. Now let me write the general equation first for total differential. In our case now, let me write, recall, you have these equations, right? So this is, we are just still using the same over and over same equation, but different in some of terms of the concept. Okay, and then we can rewrite this in terms of differentials. So this become the delta, but I will write in terms of dz, which means it's really small. Okay, and let me write this is in terms of partial x dx, and then partial y dy. And to make things more in line with classic differential, like in many subjects that you will learn, maybe perhaps we can also rewrite this in terms of the Leibniz notations. This Leibniz is expression for partials. Okay, so I hope you still remember that this Leibniz is expression for every partial terms. Okay? And d is the differential terms. Okay, so this will be the general equations. Okay, and if you observe, sorry, observe on some point AB, our dz, we can place in our AB here. And then we can say that we can have linear approximation. Okay, or we can say that this is our z, okay, and this is our initial z, the z0 at the very beginning, and this is, yeah, the dz, how much it will increasing. Okay, okay, now to visualize how it looks like and why we need to calculate the differentials, let's see this part of the picture here. Now if you look at, we have a surface z here, okay? And this is change the color. This is a point that we want to observe, okay, in the surface. And at that point, we can make our tangent plane, right? This is the tangent plane here. Okay, Now let's see what we have here. So first, of course, if you see here, the point is based on this coordinate here, and plug in the coordinate. We have the z0. Let's say the z0. This is the z0, right? So this is x0, y0, z0, right? Okay. And then we have a delta in terms of x. We have also in terms of y. That is the change of length in x-axis, y-axis, and when those delta becomes really small, getting close to d, we can see here that there is still gap here, right? So if you look at the the farthest point that in this picture is this point, right? So that means we can see that it has some gap. Okay. But when you are looking at this here, maybe here, it's getting closer, closer, and closer, right? So the gap is getting closer. So that is when your delta approximately getting closer to the d. Okay, it's really really small. Yeah, yeah. This is a tangent plane. So basically, what we are going to do in this whole tangent plane and linearization is we are just using the same plane equations, but with different approach. Okay. Okay. Now let's have some practical uh, exercise. So like let's say we have um, functions. Okay. Let's say x y squared. If you want to write down in terms of differential, the differential, the total differential will be, we can write, this is in terms z, right? It is x y squared. We can write z differentiate become dz, and then we can just write down the partial x become y squared, and then dx, and then partial y, and then dy. And this is becoming our equations for differentials. Okay, if it's asking to approximate change in z, okay, let's say from I'm giving you just easy calculations so that you can see what we are going to do here. So what we are going to do is we just let this point inside the dz. The dx means the difference on x-axis. So 0.503 minus 0.5 is 0.03, 0.003, and then plus, write down this equation to multiply by 0.5 divided by 1, and then multiply with the difference in y. And we will have 0.007. And we are seeing here that this is z increase positively, right? So if you have maybe this in terms of maybe 0.997, and maybe this is 0.499, maybe it will be negative, so it will be decreased. It can be. Okay. Okay. If we compare the true value of delta z, so delta z will be, we just plug into the real equations. This is the, the coordinate, and minus the initial coordinate is 0.5 and 1. So it will be, if you check the results, it will getting close to, oh, it should be, I think it should be approximate. Yeah. So I think it's good approximations. The accuracy is 0.00001, right? Around 5. The difference. Okay. Okay. In calculus 1, you have that maximum minimum value, right? And then you have the, usually the exercise or the examples are like, you have the box and find the largest possible value, blah blah blah, right? Okay. Now in calculus 2, we have also the same with differentials, which means it can be more than at least 2 variables. It can have more than one, like 3 or more. Okay. Well, let me give you some example, and maybe I'm just giving you the exercise in chapter 14. If we have time, we can have some exercise, but maybe next week exercise. I will focus on some chapters now. Okay, any questions from here? Okay, so basically this is similar to the linear part as we mentioned before. Okay, yeah, thank you. Okay. Okay, now all this thing here is we can solve in terms of differentials. Okay, so I think it depends on which case you are solving. If they want to, if they want you to write the linearizations, then you need to write the equation of the plane. Okay? But if they want you to write the differential equations based on the function that they give you, then this is the way that you are going to work on. Okay. But basically, the differentials, we are going to solve some a little bit complicated cases, because you need to read the words by words how the situations going on. It's like related rates, maximum value, minimum value problem. Okay. Well, let's go to the next page, and let me give you some example on what cases that we are going to look for. If the dimension of rectangular boxes are 75, let's say 60, and then 40, and then each measurement is correct within 0.2 centimeters. So meaning this is the error, okay? The error that it has, okay? Use differentials to estimate largest possible error when volume of the box calculated. Okay. Now you have three measurements here. Let's say this is just x, y, z to simplify the process. So first is every time you read questions like this, first you need to find formula, right? Similar to what we are doing in calculus 1, maximum minimum value. So we need to define the formula. Okay. Usually what previously we did, we just differentiate, right? We differentiate either it's maximum or minimum case, right? But we just differentiate and then use the conditions, and then you write the calculations, and you get the minimum or maximum value that possible, right? But now we just need to find the partial. Find partial that relates to the formula, and then evaluate. Which means there will be some cases that we need to define which one is the constant, which one's the variables, okay, that part. But I think this question here is it's just a basic questions that you, basically what steps you need to work on. Okay. So first, define the formula. I think formula is just the volume. Right? So volume is just, in these cases, it's just x, y, and z. Right? And because each measurement will be having a plus error, so all three will be our variables, right? Okay. And then we are going to have our partial, which means we will have dou v, dou x, and it's equal yz, right? And we have dou v, dou y will be equal xz. And we have, lastly, dou v, dou z, it's equal xy. So we will have all these terms. And we can write down the differentials. So this is how the differentials work. So it can help you to solve some problem that need to be estimately calculated by approximations, okay, due to maybe error, or you want to know how to maximize, how to minimize the error itself, right? So write down the differentials. Okay, and then based on what we have learned here from the questions, all the measurement, they have an error 0.2. And based what we have also knew before, that the x, dy, and dz is actually the error itself, right? From our picture here. We still have this, all this is our error, right? We have this and this. All of this d will be our error, our definition of error. So we just plug in that 0.2 inside our equations. So this is 60, 40, and then 0.2 plus 75, 40, and 0.2. And lastly, If you calculate, you get around this number. If you compare this into the real value, let me just write this. It will be having approximately 1.1% of error. Right? This is percent error that is that might become the largest possible error. Yeah, of volume of the box. Okay. Yeah, we will have some exercise, but maybe next week. Okay. So let me continue into 14.5. Okay. But before that, I hope you get the idea for these parts. Especially, so the idea is just making these two parts here. So find the formula, differentiate, partially differentiate, and you have this. And write down the differential equation. And then solve by that equations on what you want to measure, you want to find. Okay. Okay. Let me continue on. It's 14.5. So 14.4, it's end. We finished that. So 14.5, this is called the chain rule. And I hope you understand what chain rule means, okay, from the calculus 1. So I think also in chapter 10, we learned the parametric, if you remember the parametric. If we have dy dt, this is, we can explain in terms of the chain rule. And then in chapter 10, you have the dy dx as the tangent that you want to find, right? And basically, you can recreate this formula. But what we are doing here is chain rule, right? Okay, now in calculus 2, we have the formulation of C equal functions of x and y. Okay. Now, we have a new variable z, right? And the variable z is actually function of x and y. So let's check let's replace x with the parametric. So let's have the x replaced by xt, y with yt. So x is having a parametric t inside. So we can write the z in terms of x with parametric t and y with parametric t. So this means z will be expressed, right, as a function of single variable t, right? It can be any variable, but for this case, to make it familiar to you, let me just write in t. Okay? So based on what we did before in differentials, okay, so that's the core concept. So we can try to partially differentiate and write down with chain rule. So dz, but because z is now having an expression of t, we need to also divide by dt. Okay, and then the partial x, right? And then dx and dt plus partial y and then dy dt. Okay, I think this is not too complicated, I hope. So this part is basically our partial, right? Okay. So to make it familiar, let me write in terms of some example. Let's say we have z equal x squared y minus y squared. And our x is sine t, and our y is e with power of t. Then the questions is find dz over dt at t equals 0. Okay, we can start to find the partial first from the c equations. So we can write dz over dt is find partial x to xy and then or let me write the this first to make it more clear. Okay, now let me use this. This is 2xy, and then dx over dt is from sine t becoming cos t, and then plus this will be x squared minus 2y, right? And dy over dt is just e with power of t. And now it's up to you. You can just replace all with function of t, or you can replace x and y, and then you can evaluate this with t equal 0. And then use this 0 and 1 into the equations. Both are resulting the same case. But let me write in terms of making all with function of t. So 2 sine t, and then e with power of t cos t, okay, plus sine squared t minus 2t, and then e with power of t. And then let's express all with t equals 0. So dz over dt will be, this whole thing will be 0. This is 0. This is 1. So it's only negative 2, right? Okay. I hope you get familiar with the differentials, and now we have chain rule to make it. It's kind of complicated, but if you see the patterns, it will be not too difficult if you know the pattern. Okay, that's the chain rule. Okay, and it can be more than 2, 3, 4. It can be in any variables, actually. Okay. Okay, um, let me write some W like that, and let's say it has functions of x1, x2. It has a lot of variables like that. And if you want to make it in terms of partial, and with chain rule, we can make it wait, it's wrong. So it should be x1. And you can have more and more and more variables. And there is a way to how to define or how to um, map Okay, so we can map the general into a diagram. So we call that tree diagram. This is one way to look at the functions. Okay, so for example, this is the very basic case like I mentioned in previous example. So x and x is a function of t, y also the same, but both x and y is variable of z. So we can write this is z, the first terms for all variables, right? And z has two variables, right? X, y. X having t, y also has t. So we can write this in terms of first, this is partial from z, right? And this is the chain rule to make it differentiate with the respect of the variables. But it can be if you have another variable here. So it will be another partial here. Okay, got it? Let me give you some example on how we are looking at this, the tree diagrams. So example, you have this same, but you have x is having two variables like that, and y is also having two variables like that with u and v, right? Let me write v more clear. Okay. So if you want to make a chain rule, okay, what will be for dz and du and dz dou z dou v. And how to start with? First, we can map all the variables. So we start with z. Z is having two variables, x and y, right? And x is having two variables, u and v. while also having u and v. Okay. And now we have dou z, dou x, and dou z, dou y. Okay. And then this will be another partial, dou x, dou u, dou x, dou v. And this will be dou y, dou u, and this will be dou y, dou v. Okay. Now the one that we are looking for is dou z, dou u. Okay, and then dou z, dou v. So let me write dou z, dou u. And how to make dou z, dou u. Okay. First is set the dou z, dou x, and then dou x, dou u. Hey, wrong. Should be x, sorry. And then plus dou z, dou y, and then dou y, dou u. Okay. And then dou z, dou v will be dou z, dou x, dou x, dou v. So maybe, let me finish this first and let me draw what I mean. So we need to find a way from z to u here, and from the c to v here. Okay. So you can have a line here and there, and here and there. So this means we need to multiply dz dou x and dou x dou u, as we can see here. Okay. And also dou z dou y and dou y dou u here. Okay. This is 1, 2. So 1, 2. And also we need to make a way, we need to find a way from here and here. And this is, let's say, 1 here. And also the other way is here. So this is 1 and this is 2. Okay, get it? Okay, I hope you get it. Okay. So every partial or every function of several variables, 4, 5, 3, and you can have like maybe from the z you can have, or maybe not z, maybe w, f, x, y, c. Maybe this is uv, uv, and uv, and here is st, st. It might happen like this. What you need to do is you need to find a way. Maybe you want to look for dou s. So from this w, you need to find s. Okay. I need to find a way. Here, 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 and here, and also here, 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 and also here. Okay. So you need to find a way to look for the chain rule you want to compute. Okay. And it can be as complicated as it can be. Okay. So yeah. So that's the way. But I think, okay, if you look at the form itself, what I need to do is you can actually develop without mapping any tree diagram at all. Like we need to make dz and dou z, dou u, right? So first, because z is function of x and y, the first thing is you will have this x and you have this y, right? And the second thing, you need to multiply with something that it will change the result into your what you're looking for, right? But okay, if uh, if the variables is like really a lot variables and you think you need to map the variables, then the tree diagram, I think it's safer safer options for you to make sure that your partials is correct. Okay. I think I can give you one more example, and then we can let me check. Mm, yeah, we can finish for now, and next week we can finish the 14.5 and move to 14.6. Okay, let me give you the other example. So if we have, now I'm giving you an equations, and okay, I hope it's not too complicated. Okay, the question is fine. This partials. You can. I'm giving you several, maybe a couple of minutes just to think. Yeah, the answer will be the equations. Okay, so what's the equation from this partials? And I think if you are maybe in the future, we'll be working on more of codes and a little bit programming, and maybe it takes a lot of mathematics for the notations. I'm suggesting you to learn the latex, how to write that. This is to how to write the all the math notations, or any sort of programming that need to have uh, some computations. I think that will be useful for you. So yeah, because I also learning a little bit of how to write some math notations in LaTeX. Okay. The equations. So first, maybe I'm writing the diagram. So W, sorry. So W, and then we have X, Y, and Z, right? So we have three. So X, Y, and Z. So we are not sure about X, and it doesn't it's not explained in the information. So we are just using Y is going to be X, and X is actually the last term in the hierarchy, right? It's the lowest, right? And let's define all the partial. This, and if you just only having one, so it's just a normal derivative. So it's just dy over dx and dz over dx. But if you have a branch, that's is when you are using the Leibniz notations, the partials. Okay. So we are looking for this. So W and X. So we need to look for W and going to be X, going to be X, and going to be X. And that is the root that we are going to work on. So W and X. So first is this, right? Second is this. The third is this. So let's just write okay, and we can compute from this. We can compute this, but let me just write first. So let me write here. W and X. So it's just Y, right? So it's the constant, so it's just Y. Plus W to Y, it's X plus Z, right? And dy over dx is cos X. And then plus, this is only Y or Z. And dz over dx is just e to the x, right? And if we want to look for all terms into one variable, we can just change y, z into the x equation. So y is sine x, z is e to the x, right? I think we can stop just until here. Or if you want to grouping all the same like sine and sine, or maybe with e if you want, based on your preference, that's okay. But I will just stop here to just stopping the equation just until here. Okay. Okay, I hope you get the idea. Okay. I think the tree diagram is not too complicated, right? You just need to work on to find a way, like playing a game, right? You're playing a game. So from this first level, and then you need to look for a way to make it to your target. For example, this is X as your last or your finish, right? Your finish line. Okay, any questions? If not, you can leave the meeting if you want, or if you want to write the questions, I will wait several minutes if you want to write down in the chat box. And don't forget, so from now, every week, our lecture will start here in the Google Classroom meeting. And I'm not sure who is the first one who get into the Google Meet. Okay, so the first one who will get into the Google Meet, the recording will be stored in those student cloud drive. Okay, so I'm hoping you can check your drive whether you are having a new file at your recording, but I will check usually because it will be shared to everybody, the recording. I will check the file, and if some one or one student's name is appearing, and I will email you. Okay, so please check the email later. Okay, if you, I'm not sure who is the first one the going inside this Google Meet. Okay, but I will contact you later if I have seen the file in the drive. Okay. Okay, so if there's no questions, I will end this Google Meet. Thank you for your attentions. Okay. Yeah, the approximations. What you want to ask? Oh, it's because last questions. This last questions. Last question is this the chain rule or which one? So for the approximations, y dx will be that 0.02. Oh, sorry. Here. So it is actually the information is from the questions. So for 0.02, it's mentioned that the error should be 0.02, and each measurement, it says each measurement, so it will be dx, dy, and dz. Okay, and dx, dy, and dz is actually in terms of what we learned before. It's the error, right? Did you get it? Here, let me show you the here. It's 0.2 actually. So each measurement is correct within 0.2. So 0.2 will be the biggest error can that can have for each x, y, and z. Okay, so we can set the error as our dx, our dy, and dz. Is that what you are asking? Yeah, and I think the case can be different. Like maybe in other case, maybe it will be details like because it's just saying each measurement, but maybe in another problem they will say only x. So it means you only put that 0.2 only to the x. Y and z will be different. Uh, it depends on the questions actually. Okay. Okay. Any other questions? Any other questions? If no, then thank you for your attention. We'll post the information that I told you at the very beginning, and also I will upload the exercise for the chapter 14, so you can look up chapter 14 if you want, having your own exercise. Okay. If what do you mean the range? You mean percentage, or the topics? You mean the topics? Yeah. So the topics will be, so because we are now in chapter 14, so every time we are finishing, like for example, today we finish 14.4. So I hope 14.4, from 14.1 until 14.4, you have some background, because I think 14.1 and 14.2 is very basic. So I think 14.3 and 14.4 uh, will be a typical question for you. 14.1, just some introduction of functions, right? 14.2 is the introduction of limit and continuity. It's very basic. But the partial derivative itself is 14.3. So because you already have learned 14.3 and we now finish 14.4, that will be uh, the topics. I will let you know the topics uh, in the post later. I will post. Okay. Okay. If there's no questions, then we can stop the class and you can leave the meeting if you want.